Hello, so today we'll be talking about just a bit of introductory physics really. So we'll be exploring what is a wave function and how do you go about quantifying a state and writing a state of a system mathematically, where a state describes what are the known properties of the system and writes them down in a form where we can calculate how the system will evolve based upon that description of the system. So when looking at the state of a system in quantum mechanics, we want to represent the state using vectors, where vectors are something that has a magnitude and orientation. So the magnitude of the vector corresponds to the total probability contained within that state. So that is, what's the total probability of finding a system in a sub-state, if you like, that is contained within that state. Whereas the orientation tells me what overall state we're dealing with. But the way that we mathematically go about describing a state a bit more rigorously is we use an operation called the inner product. Now here I've got the inner product in terms of, alpha and beta Greek letters, where alpha and beta are vectors, and we're taking the inner product between the vectors. Now, the inner product is an operation which is defined by the three properties listed here. So firstly, the inner product is commutative. So if we flip around alpha and beta, then taking that scalar product will be the same as if we took the scalar product of alpha and beta. Sometimes I'll be calling the inner product the scalar product. The scalar product is a particular type of inner product, but you can use the words interchangeably. So we have the inner product between vectors, and the inner product is firstly commutative. Another thing that the inner product does is if we're multiplying one of the vectors by a constant, let's say a, then taking the scalar product of another vector with the vector when it's scaled by a is the same as multiplying a by the scalar product of alpha and beta. So we can take constants out of this. And lastly, the scalar product of a vector with itself must be greater than 0 if the vector itself is not 0. And for all states of physical significance, they are greater than, where they are not equal to 0, and therefore the scalar product of the vector with itself must always be bigger than 0. There are cases where you're kind of talking about how much one state overlaps with another, and if those two states are different, then they might have different vectors, in which case the inner product between them can be 0, but the inner product of a state vector with itself is always bigger than 0 in physically significant cases. So now how do we go about really constructing the state of a vector? How do we go about describing the system in terms of state vectors? Well, the inner product refers to probability, as I mentioned. It tells me how likely is it that I'm going to measure a system in one of the substates that that state describes. And the basis vectors, which we use like Lego bricks to build our overall state vector, typically are allowed classical states. Now I say allowed because in quantum mechanics only certain classical states are allowed. You can't have any state that you could in classical physics, and that is what makes quantum states special and meaningful. They're kind of building up from allowed classical states. So we have the vectors, which refer to the states of the system, and the inner product, which allows us to calculate probabilities of finding our system in a particular substate. So that's a kind of summary of the maths we'll be using. So now we finish this presentation and this kind of video by talking about how we describe a coin quantum mechanically. So a coin, if it's lying flat on the table, it can either be in heads or it could be in tails. The allowed classical states are heads and also tails. Therefore, because the coin can only be in heads or tails, at least in classical physics. But in quantum mechanics we can have superpositions of classical states. So we can describe a state which is kind of made from adding the classical state of heads to the classical state of tails. And we can write something like this. Now, the kind of coefficients here, these coefficients next to the capital H and capital T are numbers which refer to the probability of the system in this quantum mechanical state being found in the corresponding classical state. So we see that the coefficients behind the H and T states are the same. They're both 1 over root 2. Therefore, what this is saying is we're equally likely to find the coin in heads as we will be to find it in tails if initially, before measurement, it's in this quantum state. And we call this kind of adding of classical states superposition of classical states. Because it's sort of both simultaneously in a manner of speaking. Now, here's where we bring in the scalar product or the inner product and start to think about how this works. So heads and tails are mutually exclusive classical states. That is, if a coin is in heads, there's a probability of 0 of measuring it in tails, because it's impossible to find it in tails if it's in a state of heads, and vice versa. Therefore, the inner product between H and T is 0. So H dotted with T is 0. Similarly, due to the nature of the inner product, T dotted with H will be 0. And again, that's because the classical states are mutually exclusive. Now, kind of the opposite of that, if you like, is thinking about the probability of finding the coin in heads if it's initially in a state of heads. Well, if it's initially in a state of heads, the probability of finding the coin in a state of heads immediately is 1, because it's definite, and the same thing is true with tails, and that's true by definition. If a coin is in a state of tails, then we will measure it in a state of tails, assuming nothing happens to the coin to change its state. Now we can use these two facts, the mutual exclusivity of heads and tails, and the fact that heads dotted with heads is 1 and tails dotted with tails is 1, to work out what the scalar product or the inner product of our state vector psi with itself will be. And using the kind of two properties of our classical states, we find that the inner product of our state vector dotted with itself is 1. And this refers to the fact that this refers to the fact that if the coin is initially in the quantum state psi, then the probability of finding the coin in one of its substates, so heads or tails, upon observation is 1. It's definite. And we therefore say that this state vector is normalized because the inner product of it with respect to itself is 1, and because of the two properties of the kind of classical states that we mentioned, so the inner product between H and T equaling 0 and the inner product between H and H or T and T equaling 1, we say that these classical states are orthonormal. So we've used orthonormal classical states, which comes naturally about thinking of the nature of heads and tails, to work out the inner product of our state vector with respect to itself, and we found that we have a normalized state vector. And because it's definite that you're going to measure a quantum mechanical system in one of the classical states that make it up, so in one of its basis states, if you like, because it's definite, all valid state vectors have to be normalizable. That is, there has to be a way to make them, when doctored with themselves, equal to 1. And this introduces normalization factors. And normalization factors allow us to work out exact probabilities. But that's all for today. So today we talked about how we describe a system quantum mechanically using the state vector. Next time we'll be looking onto deriving the idea behind Heisenberg's uncertainty principle and getting an understanding for how we represent the evolution of states when the state starts to evolve with time or with respect to some other parameter. So see you there. Hope you find this video enjoyable. If you have liked it, please hit like, and I hope to see you for the next video.